Yeah, so we were talking about Lewis structures, and Lewis structures are kind of a two-dimensional shape. But what like reality do we live in? How many dimensions do we see?
Three.
Yeah, we see three. Some people think there are multiple dimensions. That's for theoretical physicists. We're not going to worry about that. So how do we live in a 3D world, but we draw these 2D structures. So what we have to do now is we have to work on your guys' three-dimensional spatial arrangements so you can actually see what the molecules look like on the inside of your head. That way, if you know like what the three-dimensional shape is, you can predict a lot of different properties of these molecules. So to do that, we're first going to have to look at something called molecular shape. So we're going to move on. This is in the last chapter that we're going to talk about. This is primarily in chapter 9. Let's see if this thing will focus. Yeah, there we go. So chapter 9. And what we're going to discuss is molecular shape. Okay. So we know that the shape of molecules is 3D. But when we draw those Lewis structures, they're two-dimensional, right? They're flat. So we got to have a way to try and translate between these two. Lewis structures are 2D. So we're going to use a different model to explain what these shapes are. And you might have talked about it in high school or in your AP courses. And it's known as the Vesper model or a valence shell, electron pair, repulsion, or Vesper model. And what this model can tell us, it can tell us the three-dimensional shape of a molecule. It tells us 3D arrangement. And how do we figure these things out? Well, what you have to consider, you first have to determine what are the number of effective bonds. So shape is determined by number of effective pairs bonding pairs and lone pairs. And can somebody tell me what I mean by lone pairs again?
Unbonded electrons.
Yeah, non-bonding electrons. These are ones that are not involved in bonds. So I use these synonymously, as you can tell. Okay, so let's talk about what do we mean by an effective pair? And what we mean by an effective pair is it's just a region of electron density. So it's a space where electron density is sort of confined to. Each effective pair and each bond, whether it be a single bond, double bond, or triple bond, is worth one effective pair. So one lone pair of electrons, that's going to be equal to one effective pair. What about a single bond? How many effective pairs did we say that one was worth? Or what do you think? How many effective pairs will it be worth?
1.
Be 2.
Yeah, it's going to be 1. Now the tricky part is double bonds and triple bonds also count as one effective pair, one region of electron density. So double bonds and triple bonds, they're equal to one effective pair. Okay, so what we're going to do now is we're going to draw some Lewis structures, and we're going to determine how many effective pairs are around that central atom. Okay? Am I all right to move this up? Yeah, okay. So, example, determine the number of effective pairs around the central atom in the following molecules. Okay, so we have these 3 molecules. The first thing we have to do is we have to draw their Lewis structure. Does anybody know the name of molecule A, by the way, since we're doing a little bit of a review?
Methane.
Yep, that's methane. Okay, let's count up how many valence electrons we have. How many valence electrons do we have for carbon?
4.
Yep, 4 plus 4 times how many for each hydrogen?
1.
Yep, for a total of how many?
8.
Yep. Okay, so now we know we have 8 valence electrons. Which one's the central atom?
Carbon.
Yep, carbon. Okay, it's easy enough to draw out carbon with 3 bonds around it. I'll try to make those bonds a little more clear. Okay, so now we have to determine how many effective pairs there are. How many effective pairs are around this molecule? Or excuse me, around this carbon, that central atom.
4.
Yep, 4 effective pairs. Okay, after we know this, in the next section, we'll talk about how you determine the number of effective pairs, then you get an idea of its shape, and you move on from there, okay? But it's important to get this first step. B, does anybody know the name of that one? That one's known as formaldehyde. So I was actually going to be quite well acquainted with this before I decided to become a chemist. I was actually going to become a mortician. So weird habit to change for some reason. I figured it was a crummy job because all you're doing is seeing sad people all day. So I changed my mind. But okay, so now weird aside, sorry. Valence electrons for carbon.
4.
Yep. Oxygen.
6.
Yep. And then we have 1 for each of those hydrogens, right? Okay, total of how much then?
12.
Yep. Which one's the central atom?
Oxygen.
Not oxygen in this case.
Carbon.
Yep, carbon is. How do you know carbon's the central atom as opposed to oxygen?
Carbon.
Anybody know?
The least electronegative.
Or electronegativity.
Yep, lower electronegativity. So carbon has a lower electronegativity than oxygen, so it maintains in the center. So let's draw it out. Okay. So there we have our structure. I'm going to make those bonds a little more even. Now we need to determine the number of effective pairs around that central carbon. So how many effective pairs are there? Or how many regions of electron density are there?
4.
Remember, how many effective pairs is this single bond worth?
1,
1, this single bond?
2, or 1.
1.
1.
This double bond?
1.
Also 1. So how many effective pairs in total?
3.
Yep.
3.
3 effective pairs. Okay. Last one. We kind of have 2 central atoms in this case. How many valence electrons for carbon again?
4.
Yep. And then 2 for each of the hydrogens, total of 10, right? Okay. If we draw this guy out, this one's known as acetylene. It's used in welding and in a couple of the instruments that we have upstairs to get really high hot temperatures. Okay. There are 2 central atoms in this case. They're both the carbons, right? But we're just going to look at one of them. How many effective pairs are around this carbon?
2.
Yep, 2 effective pairs. Okay. So that gives you an idea of what the effective pairs are and how to diagnose them. Does everybody feel comfortable or feel like they can do that? Because you need to have that skill before we can continue on.
I have a quick question.
Yeah.
So within like the last one we just did, how do you know which carbon to use since they're both?
You could look at either of them. And in reality, like when you look at the shape of molecules, you have to consider each of the central atoms, basically.
Okay.
Because they can kind of connect and they build off of each other.
Okay.
Does that make sense?
Yeah.
Okay.
Thank you.
Yeah, no problem. Okay, so now we know how to count these effective pairs, but how do we get to a 3-dimensional structure? So that's where we have to jump back to that Vesper model. So we got Vesper. And by the name of this model, what we're going to assume is the electrons repel each other. So we know that's true, but electrons repel each other. And what happens are the bonds and the lone pairs move as far away from one another as possible. So they're trying to reduce that electron-electron repulsion. So bonds and lone pairs move as far away from one another as possible. So they're trying to move away from one another as much as they can, so spatially they're stacked out away from each other. Okay? So what we're going to do now, we're going to build the table. Am I okay to move this? Okay. So now what we're going to have, there's a very similar table in your book. What we're going to do is we're going to keep track of the number of effective pairs. We're going to keep track of something called the electron pair geometry. And then we're going to have some examples. Try to move up a little bit. Okay, and what we're going to do, we're going to keep track of 2, 3, 4, and 5 different pairs. So we're going to have 2 effective pairs. Let's pull up a model of what this will look like. So I've built some models in a program called Avogadro, which is free and available if anybody else wants to use it. We do also have an app for our general chemistry class called Bana's Bond Builder. You can download it on any device, and it allows you to like build molecules drawing the Lewis structures, and then it will show you a 3-dimensional representation on your phone. In this case, I'm using a program that's a little bit different. It's known as Avogadro. And I will share it right now. Okay, can everybody see my screen? Okay, so this is a carbon monoxide molecule. And what we're going to do is we're gonna try to describe the shape. Does anybody know what this shape is?
Linear?
Yep, it's linear. So we're gonna make note that the electron pair geometry is linear, and we're gonna try to draw this molecule out. Before we do that, can anybody tell me what the bond angle is? Like if I measure it from like between these atoms, does anybody know what that angle will be?
180 degrees.
Yep, it's 180 degrees. So we're going to try to draw that out on the paper. There we go. So we have linear. We'll do A, B, A, like that. And we'll want to keep track of that bond angle. And what did we say the angle between these molecules was?
180 degrees.
Yep. Okay. And we had an example that I just showed. Does anybody, what was that example? Or can you tell me another example of a linear molecule?
It was carbon monoxide.
Yep, carbon dioxide. And then,
Dioxide.
yeah, that's okay.
Sorry,
And then,
yeah.
then another one like beryllium chloride would be another example. Okay. All right. So now let's move on to 2 effective pairs, or excuse me, 3 effective pairs. 3 effective pairs. Again, I'm going to share my screen with you, and we're going to try and name this guy, and we're also going to come up with the bond angles, all the unique bond angles in the system. Okay. So if you look, this is the 3-dimensional shape that we get. Okay. Does anybody happen to know the name of this shape?
Trigonal planar.
Yep, it's trigonal planar. And do you know where the name planar comes from or what that means?
It's on a 2-dimensional plane.
Yep, exactly. It's flat. It's 2D. So wherever you see the word planar, that means it's flat. Okay? So can anybody tell me, like if I look at this bond angle between, I don't know, those 3 atoms. Anybody know what that bond angle will be?
$120.
Yep, that's 120 degrees. Okay, so let's try and draw that out. Okay, so we're going to try to go with that shape. Again, I keep knocking the camera so it gets wiggled a little bit further away. Hey, focus thing. Okay, so we got A, B, A. And we said this angle along here, what was it?
120.
Yep, 120 degrees. Okay. Could you give me an example of a trigonal planar geometry? Any that we might have seen in that very last example we did, like where we were counting effective pairs.
Methane?
Not methane. How many effective pairs did methane have?
Oh, wait. That 4.
Yep, it had 4. So we will throw that in the 4 spot.
Formaldehyde.
Yep, formaldehyde. So CH2O is an example. Another one that gets commonly used, the one that I was looking at, was boron trifluoride. Now, this is where we're moving away from these 2D shapes and we're going to start to see 4-dimensional shapes. Let's look at a 4D shape. All right, so let's zoom in on this guy. 3-dimensional shape here. Anybody know the name of this one?
Tetrahedral?
Yep, it's a tetrahedral shape. So we're going to try to draw it, but let's say I look at like this bond angle. I want to know those atoms. What's the bond angle between those 2 hydrogens? Anybody know? Sorry, I think I interrupted somebody.
Oh, I said 90.
Nope, not 90. That would be a little more square and there would be a flat point somewhere.
109.
Less than 109.
Yeah, that's about 109.5. Like, we can actually measure it and see what it says. Well, in this case, 109.5 exactly. So let's try and draw this one out. We said, what was its shape again?
Tetrahedral?
Tetrahedral. And we're going to try to draw it in this fashion where the atoms that are in the blue are in one plane. They're in the plane of the paper. We have one atom sticking out and one atom going in. So we're going to try to draw that. Okay. So we said tetrahedral. Now we're going to try and draw this. We got B, A, in the same plane. Now we have one atom coming out towards us and one going back in. And we try to show this 3-dimensionality with dashed and wedged bonds. So do A. So we're trying to show that this guy is going back into the paper. This one's coming forward into the paper to give you kind of like a 3-dimensional idea. And again, what did we say this bond angle was?
109.5.
Yep. And we already came up with an example of it, methane, right? Okay. Now let's move up. Let's go to 5 effective pairs. So we're going to pull up another model. And let me share that model. Okay. In this case, we're going to have a handful of unique bonds. Notice I colored the atoms a little differently. So the green spheres have a different bond angle between them compared to the red spheres. What's the bond angle between the 2 green spheres?
180.
180.
Yep, 180. Now let's look down the plane. What about between 2 of the red spheres?
120.
120. Now, what about between a green and a red sphere?
109.
Not 109 in that case, because that would be it would be a little more bent, right?
90?
Yep, this is 90. So, does anybody know the name of this molecular shape?
Isn't it pyramidal? Like trigonal, pyramidal?
Yep, trigonal pyramidal. Okay. And how many unique bond angles did we find here?
2.
We have more than 2. I think we
3.
had 3. We'll try to draw those out. Before we do that though, the division along here between these atoms, these are known as axial positions. And the red spheres are known as equatorial positions. So sometimes people will talk about axial or equatorial bonds. When it comes to this molecular shape, that's what they're discussing, okay? So let's try to draw that in 3 dimensions. What we're going to do is we're going to rotate this molecule where these 3 atoms along here are in the plane of the board. Then we have one coming out and one going in, okay? We're going to try our best to draw that. Okay, so we got B in the center, A. Then we have an A coming out towards us. And we have one going back in. Okay, now we're going to have a handful of unique bonds. I'm going to try to draw them in a couple different colors. Hopefully I can find blue. This blue. There we go. Okay. So now, this bond angle between an axial and an equatorial atom, what was this bond angle again?
90?
Yep, 90 degrees. Okay, now what about between 2 equatorial atoms?
120.
Yep. Okay, and finally, between the 2 axials, what was that bond angle?
180.
Yep. Okay, and an example of this, we have to think of something that will have 5 effective pairs around it. Does anybody have an idea or a molecule that they might have done in the past that had 5 effective pairs around it?
Xenon pentafluoride.
Yep. Oh, actually, xenon pentafluoride had some lone pairs around it. Let's go with a pentafluoride compound, though. Let's do phosphorus pentafluoride. Like that. Okay. The last electron pair geometry that we have has 6 effective pairs. The one that we're going to discuss, there are ones that go greater than that, but we're not going to worry about those. Am I okay to move the paper? Okay, let's do 6 effective pairs, and then I'm going to share the model with you. So this is our model. Rotate it around a little bit. Does anybody know what the name of this geometry is?
Octahedral.
Yep, it's octahedral. So for those who might have been cheating, if you notice up in the corner, all the names have been up over there. Or if you have good enough resolution on your screens. But it's also good to know them too. Okay.
I have a quick question.
Yeah, sure.
Okay, so for so say you had like 4 effective pairs, is it always going to be tetrahedral, or is it always going to be like the same thing, or is it able to change?
It is, so what is known as the electron pair geometry will be the same, but the molecular shape does change. So we will talk about that in a moment. Okay?
Sorry, I jumped the gun a little.
No, that's okay. So yeah, like what will happen is if you think about the regions of electron density, those regions don't really change that much. But then when you start chopping away bonds and replacing them with lone pairs, then that shape begins to change. So we'll talk about that in the next section after we get done with this guy. Okay, so looking at this, we again have axial and equatorial bonds. But is there really a difference in this case between the axial and equatorial? What is the bond angle between any two adjacent blue spheres? So like between these two guys, what's that bond angle going to be?
90 degrees.
Yep. What about between this one and the bottom one?
90.
Yeah, 90. They're all 90. So what we're going to try and do now is draw this structure. We're gonna have it kind of folded like this, where these three atoms are in the same plane, and these two come out, and these two go back. Okay. Sorry, I gotta find my thingy. There we go. So let's try and draw that out. Okay, so we have B in the center, we have A, and then we have two A's coming out, and two A's going back. Okay, does anybody have an example molecule that they could think of? This one is a really cool molecule. If I ever can get a hold of it, it's fun to play with. It's sulfur hexafluoride. Does anybody know what this does when you inhale it?
Makes your voice really deep.
Yeah, it makes your voice super deep, like comically deep. Normally, when we have in-person classes, and if I can get a hold of this, I ask if there is somebody with a high-pitched voice that can do a handstand, because the problem is if you inhale it, it's so dense, it just sits in your lungs, and you'll actually pass out from oxygen deprivation. But while you talk, it's comical. Like, your voice gets so low. You know how when you talk, you feel like your voice is kind of right here, you can feel it. When you inhale this stuff and you talk, you don't feel that there. It feels like a completely foreign entity. So I'll send out a video of it, of somebody inhaling it, but it's pretty funny to hear. So, okay.